Hello, welcome to Module 3. So in Module 3, we're going to discuss some basic principles that are related to software analysis and testing, model-driven test design, and the activities of the test engineers. Okay, so in this module, you learn some basic principles that are underlying for the analysis and testing techniques, and then grasp some motivation of these principles. And we will also discuss the principle called model-driven test design, and also what the software engineers that are quality assurance engineers are doing in practice. So let's get started by discussing about the cause of software bugs first. There are many studies that try to see how much software bugs can cost, and there are a lot of costs that are involved. Okay, so the first one occurred in 2002 by NIST in the US. They found that in 2002, the cost of software bug is around $60 billion per year. That's only in the US, which is a huge amount of cost, right? The second study is done in 2012 by Cambridge University. And this is a study for the whole world. So Cambridge University studied the cost of software bug worldwide. So in 2012, Cambridge found that $312 billion are the cost of software bug worldwide. In 2018, this is 18. Another organization called CISQ also did a study of software bug in the US alone, and they found that the cost of software bug is $2.8 trillion. So if we compare these two studies, the cost of software bugs after 16 years has increased a lot from billion to $1 trillion. There is also another study of software failures in 2017. Okay, they studied 314 companies with 606 software failures. They found that the amount of cost of these failures sum up to $1.7 trillion. And it affects 36 billion people around the world. And if you accumulate all the downtime of the software, that could add up to 268 years. Okay, so another things that are important and I want you to pay attention to is the cost of software bug in each software development life cycle. Okay, so the software is created in many phases. So we start from requirements, we do implementation, we do integration tests, we do system tests, and then we deliver the product. This chart shows how much cost is created when you found a bug and you fix them in each particular phase. Okay, so these are the costs, which is a relative cost. Let's say we don't put it in a specific currency or so, but we're going to use Thai baht here just as an example. So if you find a bug during the requirement phase, let's say we need to pay for fixing that bug for $1. Finding the bug during requirements is not very difficult to fix. You just need to readjust the requirement text, and then you make sure that it is correct by checking with the customers, right? So if you leave that bug until the coding phase, the cost that you need to fix the bug is around $5, right here. And you will see that this increases the cost by 5 times. If you leave the bug undetected until the integration testing phase, when you try to include multiple modules together and check whether it works together correctly, that would cost you 10 baht, okay, which is twice of the cost that you would do if you find a bug and fix them during coding phase. And if you leave the bugs until the system or acceptance test, that would cost you even more, around 15 baht, which is 1.5 times higher than the integration testing time. And lastly, if you leave it until you have deployed the software, go to production, and there are already actual users that are using your software, they found a problem, they report it back to you. The cost of fixing at that point is very high, 30 baht. So think about getting the software fixed, and then you need to release the new version of the software, and the user already found a problem. So you might have some cost for reputation of the product and also the company, so on and so on. So in this case, it is twice the cost from the system test. And if you compare from the very first phase of the requirements, that is 30 times higher than finding the bugs earlier in the requirements phase. You will see that this cost keeps growing exponentially over the life cycle phases of the software development. So there is a concept called shifting left nowadays, which means we need to find the bugs or the faults in the software early on in the very first phase. So during the software development lifecycle, the team must start looking for potential faults or issues since the requirements. Make sure that the requirements are as most correct as possible. When you move to coding, you do unit tests to make sure that the code is correct. When you do integration of the module, you do integration testing, and then you do system tests to make sure that before you deploy, there is as few bugs as possible to reduce the cost. Okay. And also the amount of code is increasing over time. Okay. You will see that the amount of code, it has, let's say 1,000 lines of code written. There would be 100 to 150 faults here. There will be 100 or 150 faults for every 1,000 lines of code that you have written. And the amount of code usually doesn't go down, except you do some refactoring or you remove some of the features. But usually the code keep increasing. So that means also the amount of fault in the code that you just added also will be higher and higher. So testing becomes even more important when the software is growing and getting bigger. And next, I would like to discuss the principles that we will use to guide our software quality assurance and testing activities. This is called analysis and testing principles, which can be divided into two groups. The first one is called the general engineering principles, that are principles that can be applied to any engineering processes. And the second one is called specific analysis and testing principles that are applied specifically to the software testing only. For general engineering principles, we have partition, we have visibility, we have feedback. While for the specific A and T principles, we have sensitivity, redundancy, and restriction. So let's see each one of them in detail, starting from the general engineering principles first. The first one is called partition. When we have hard problems, we usually divide and conquer the problems to be smaller ones. And then those divided problems are smaller and it's easier to manage and handle. So the same thing, if you have difficult testing or verification problems, you can make them easier by partitioning them into smaller chunks. If you still recall the first example that I showed in module 1, you want to find the value that you want to test the sum method. And we can see that the amount of potential values are huge. So we can apply this concept of partitioning to chop the value of the parameters into partitions, and then we deal with each partition That makes the problem easier. So in the next few modules, we're going to study how we do this kind of partitioning and how can we find the group of similar data and group them together. What are the techniques that we're going to use to determine such partitions? All right. The second principle is visibility. So visibility means we should be able to judge the status of our work against our goal. Okay. So how could we measure the progress or the status that what we are doing against the goal? So for software testing, it would mean how many percent of code that are tested. So we're going to study in the next few modules as well the concept of coverage criteria. How would we define the coverage so that we know the status of our testing? Okay. But for other engineering activities, you might ask yourself, are you behind or ahead of the schedule? So this is something that we need visibility for. Or how do we know that the quality of our product meets the objectives that we set? So first thing is we need to set the goals, and then we need to assess the progress at each step so that we know whether are we getting close to the goal or not. The third principle is called feedback, which means you get some information from the previous iteration and use that information to improve the next round of your activity. We use this feedback in testing as well. So when you do testing and then you know there are some problems that you found from the test, you can include that information so that you can avoid a problem in the future. Okay. So we use the information to improve the next round of our testing process. For example, you can create some checklists to make sure that the errors or the fault that we found in the past is not being created again in this round. Or you can create some errors taxonomy that will help you to create a better test case selection. So if we know that there are some specific faults or errors that occur a lot, then we can target our test to those specific fault or errors. And you might create some design guideline so that you can avoid some common pitfalls that you have done in the past. All right. So these are the general engineering principles. Next, I'm going to move to some specific analysis and testing principles, and there are 3 of them. The first one is called sensitivity. Sensitivity means it is better if the software fails every single time than sometime. For example, if you can locate the actual cause of the software failure, you want that software to also fail every single time if you give that input and trigger the fault. It would be more difficult if the software doesn't fail every single time. For example, if you find that if you give an input of 10 and then the software fails the first time, and then you give the input 10 again, but the second time it doesn't fail, and then you give the input 10 again, and the third time it fails, that would be really difficult for you to pinpoint the actual fault in the code. So sensitivity in this principle means the software should fail every single time if you give the same input that trigger the fault in the past. Okay. So some of the software can be non-deterministic. And if you have non-deterministic software, then the software might not perform the same behavior every single time. And this can create some issues, for example, a race condition. One case study that occurred in the past is Facebook IPO. Okay, so the Facebook company at the time, before they changed the name to Meta, they were getting into the stock market in 2012. So in 2012, on the day that the Facebook stocks are being sold, many people were interested in the stock, and there's a lot of people putting in the request to buy the stocks. And Nasdaq, which is the stock market that are selling Facebook stock at the time, their software has some problem called race condition, which means you have many processes or many threads that try to get into the same resource at the same time. In this case, the allocation of the Facebook stock. And the software has some unpredictable behaviors, and there are some wrong results created. So some people receive more stocks than they supposed to, and some people didn't get the stock that they are requested for. So in this story, the Nasdaq's market might need to pay about $13 million to compensate for the traders for this problem. So this problem shows that for the software that has sensitivity issues, it fails sometime and it doesn't fail sometime, then it is difficult to do the test. I'm pretty sure that Nasdaq has already tested the software, but the amount of requests that are created in this specific event might be more than what they did the test or what they would expect it. That create this problem. The second one in the AT&T principle is called redundancy. So redundancy is when you do something similar over and over again. We did that intentionally because we want to increase the capabilities that we would find faults in our software. So we did a lot of tests in the software development, which we're going to talk about during this whole course. You start by unit tests, and then you do integration tests, and then you do system tests, and then you do user acceptance tests. So you perform both verification and validation on the same software many times, so that you are making sure that all the possible faults are catched early on in every single steps. Okay. The last one, the last principle is called restriction. So restriction is when you put some suitable restriction on your problem, it might make the problem easier. For example, sometimes if you put a weaker spec, it might be easier for the problem. Imagine the programming language, C or C++. You have pointers that are difficult to handle, and you can get some memory issues like core dumped. The newer programming languages like Java, Python doesn't use pointers anymore. So you weaker the spec. You make sure that the pointers are initialized every single time before it's used. Then the problem is easier, and we have fewer problems with the pointers in newer programming languages. On the other hand, if you have some stronger spec, in some situation, it might be easier. For example, if you use the programming language like JavaScript and it doesn't have types, so when you write the programs, you don't know whether there will be any fault or errors or not until runtime. So you execute the programs and then some errors might occur. But if you put some stronger spec like TypeScript that you already have types for all the variables, then some of the type problems you can detect during your coding time. So that makes the fault being caught much earlier than runtime. So restriction means you put some restriction, either it's going to be the weaker ones or it's going to be the stronger one. Select the suitable restriction can make the software testing becomes easier. And next, we're going to talk about software testing foundations.